Assalamualaikum and good evening. My name is Arifin, joined today by Fariz bin Mizan, Loh Suet Yi, and Nazerke Kashimova. So for the introduction to PCE, for the reactive unit, it consists of both carbon dioxide and hydrogen, which is then converted into methanol and water in the synthesis reactor. It is also a prerequisite in the methanol industrial production. So the fundamentals and the concepts of principle of chemical engineering, such as material balances, conversion analysis, is demonstrated by ensuring efficiency of the process, accurate mass flow and conversion calculations relies on the stages of mixing, separation, recycling, and purification. So for our non-reactive unit, we choose the distillation column. It consists of crude methanol feed, which contains both methanol and water. So for example, in our case, a 50 to 50 ratio methanol to water feed enters at 40 moles per hour can be analyzed using mass balances on the feed, distillate, and the bottom stream. So moving on to the introduction of fluid mechanics. For the reactive unit, fluid mechanics is important to methanol production as it helps with the processes for mixing gases and the transportation of gases to reaction and separation. So understanding fluid flow, behavior, and pressure dynamics and fluid properties, it ensures efficient operation and the reactor performance. To summarize it, fluid mechanics provides a foundation for designing and controlling of the methanol production system. For the non-reactive unit, in the distillation column process, it mainly involves the fluid mechanics as both the liquid and vapor phases move up and down and interact within the system. So the downward flow of the liquid and the upward flow of the vapor determines the separation efficiency, which depends on the fluid behavior, pressure differences, and the phase interaction. Understanding these principles is useful in optimizing performance and ensuring effective mass transfer.
Everyone, my name is Nazerke Kashimova and I'm going to present the reactor mass balance of the methanol synthesis. First of all, we set our bases at 100 mol per hour total feed consisting 25 mol per hour carbon dioxide and 75 mol per hour hydrogen. So this is 1 to 3 ratio. The key operating parameter here is 80% conversion of hydrogen. This means 60 mol per hour of hydrogen is consumed. Using stoichiometric ratio, we calculate that its consumption results in the formation of 20 mol per hour of methanol and the 20 mol per hour one. My name is Nazerke Kashimova and I'm going to Here is the component material balance table. It shows us that the total feed 100 mol per hour reduces to 60 mol per hour at the outlet, and it also shows us unreacted reagents and products at the right corner, also mole fraction. Now let's move to the non-reactive part. It's distillation column mass balance. So the objective is simple. It's just the produced distillate stream with 90% purity of methanol. To find the flow rate, we just set up system of two equations based on our material balance. So first one is the overall balance. 40 mol per hour feed must equal to the sum of distillate and the bottoms. And second one is methanol component balance. So the total methanol in the feed must equal to the methanol leaving streams D and B weighed by their purities. In our case, 95% and 5%. By solving the system, we get that distillate stream is 18.95 mol per hour and the bottom stream is 21.05 mol per hour. Here you can see the distillation column component balance where our feed 40 mol per hour split it into distillate and bottom, and from distillate we get our target product methanol 18 mol per hour.
Okay, for methanol synthesis reactor, the reactor convert carbon dioxide and hydrogen into methanol and water under high pressure and temperature. We assume no heat is lost to the surrounding, meaning all the energy change comes. Okay, for this slide, I will talk about reactor energy balance. I'm using his law. I substitute the enthalpy of formation value from NIST. The heat of reaction is negative 131.2 kilojoule per mole. The negative sign show it's exothermic, meaning the reactor releases about 0.73 kilowatts of heat that must be removed by cooling water or heat exchanger. Okay, now for the distillation column. The distillation column separates methanol from water by using heat. Methanol being more volatile, vaporize and rise to the top, while most water remain in the liquid phase at the bottom. Okay, for this slide, I want to talk about calculation of distillation energy balance. I use CP value from the engineering toolbox to find how much heat absorbed to the vaporized methanol and separate it from water. The column need about 0.19 kilowatts of heat input at the reboiler at the same amount is released in the condenser. Okay, in summary, the reactor release heat that must be removed while the distillation column require heat for separation. Both units balance energy differently, but together they complete the methanol production process efficiently. Okay, that's all from me. Thank you.
So up next, our focus shifts from the chemical and energy balance aspect discussed earlier to the fluid mechanics components of the methanol production process. In this section, we concentrate on how fluids move within the plant through the design of piping system, analysis of pressure losses, and selection of pumping and storage system. The goal is to ensure that the entire production line operates safely, efficiently, and economically under the real process conditions. The first part of Chapter 3 focuses on the piping layout design. The piping system connects all major units of the methanol plant, starting from the mixer to the reactor, separator, flash unit distillation column, and finally to the storage tank. So as you can see, the process flow contains major stream from feed lines, feed transfer line, reactor outlet to separator outlets, and the design aims to create a leak-tight, safe, and cost-effective flow network that supports both gas and liquid transfer at varying pressures. The flow direction is set from left to right, and each unit is equipped with pressure and temperature gauges, sampling points, and flow meters. These instrumentation points ensure that the process can be properly monitored, controlled, and maintained. Next, we move to the selection of pipe materials and dimensions. For high pressure lines, such as those connecting to the reactor feed and outlet, stainless steel 316 was selected. It provides excellent corrosion resistance and can withstand the elevated pressure and temperature during the methanol synthesis. Meanwhile, carbon steel was chosen for low pressure and utility lines to achieve cost efficiency without compromising the mechanical strength. As for the pipe diameters, it ranges between 25 to 90 millimeters, with wall thicknesses of schedule 40 and 80. Here are the details for the pipe schedule, and the bigger the schedule number, the thicker the wall will be. Therefore, it can withstand higher pressure. As for fittings, connections, and flow directions, standard fittings such as elbows, reducers, teeth, and valves are used to ensure smooth flow transitions and safe isolation when needed. Connections are flanged or welded depending on whether the joints are permanent or removable. So up next, pressure drop analysis was carried out using Bernoulli's equation and the head loss formula. This step is very important to determine the amount of pressure energy lost due to friction and fittings along the pipe. So as you can see, the pressure loss formula can be obtained by arranging the head loss formula and head loss in Bernoulli's equation to get the local pressure formula. So as you can see, for the pressure drop and pumping calculation in Chapter 3, we use all flow rates, compositions, and temperatures from the earlier material and energy balance in Chapter 2. Additional assumptions were made, including straight pipe lengths, standard fitting losses, pipe roughness, and fluid properties for both gas mixture and liquid methanol. Calculations of total feed composition up until local losses were done, and the detailed calculation is shown in the report. So after all the calculations, here's the summary of pressure drop across the pipeline. So the value are very, very small due to the small production basis. For example, in the mixer to reactor line, the total pressure drop was only 0.023 Pascal, indicating a laminar flow regime. Similarly, the pressure losses for other pipelines were found to be extremely small due to the very small production basis and also the pilot scale production. So our strategy to deliver methanol to the storage tank involves using an SS316 centrifugal pump to ensure reliable liquid transfer, supported by check valves and standby pumps for safety. We control flow using meters and level interlocks, and the piping is designed with the proper slope and venting to prevent vapor lock. Additional safety measures are like bunding, leak detection, and grounding protect against spills. As for the pump power calculation, the calculated pump power requirement was 0.0138 watts, very small due to the low production basis, but the design approach can be easily scaled up for industrial operation. As for the storage tank, it was designed as a vertical cylindrical tank with a capacity of 100 liters, providing around 5 days of buffer storage. Safety features such as check valves, leak detection, grounding, and bund walls are also included to ensure safe transfer and storage of flammable methanol. In conclusion, Chapter 3 demonstrates how the principles of fluid mechanics are integrated into chemical process design. From the piping layout to the pressure drop calculations, every detail ensures that fluids are handled safely and efficiently throughout the plant.
In conclusion, this project successfully demonstrated the core principles of fluid mechanics and principles of chemical engineering to design an efficient and sustainable methanol production process. Material and energy balance solutions have proven effective conversion of hydrogen and carbon dioxide with the selection and the sizing of the pipe fittings, ensuring the high product purity and performance. Overall, this project reflects strong understanding of the theoretical concepts and their practical application in methanol production.